Space is like a texture, elastic like a trampoline net. Imagine turning this trampoline net into a pretzel and permitting yourself to go in reverse in time. We had the option to go from Earth to the Moon across 1/4 of a million miles of space, land on the Moon, and then return to Earth. How would Newton interpret gravity? Albert Einstein, the great physicist, once said that gravity is a duplicity. Einstein committed his career to uncovering the truth of gravity, discrediting Newton's widely held convictions, and providing answers to confusing time travel questions. Why is there only one way in which time travel exists, when you travel at the speed of light? Why does time slow down? The latest speculations and discoveries made by modern physicists attempt to provide a ludicrous hypothesis of time to explain the unexplainable. Now, we should learn more about the gravity hypothesis of Newton, which contradicts Newton's attractive energy hypothesis. People didn't start to genuinely scrutinize their environment until the 1500s. The ancient Greeks believed that divine beings and gods could explain and legitimize everything, but by the 1500s, scientists like Galileo and Brahe had established that Earth was a planet, not just one in a series. In fact, the planets in our solar system circled the Sun. Kepler went one step farther and described how the planets and their moons moved along their own axis, looking like a circular orbit rather than in a definitively round circle. Newton continued this in the 17th century. The world has heard of the English physicist who supposedly discovered gravity after an apple fell on his head. However, it is now accepted that Newton didn't just happen upon the hypothesis of gravity. For a long while, he had been observing unmoving things shift from their stable positions due to some unexplained force. Yes, this also involved watching apples tumble from trees. Following several hours of study, Newton finally hypothesized that this cryptic power was gravity. He was too eager to propel Kepler's circular orbit hypothesis because of the revelation that the Moon, which is the closest celestial body to Earth, is simply able to go alongside the planet due to a straight-line trajectory that crosses the Earth's center and holds the Moon in place under the planet's gravitational pull. However, before Brian Cox began testing Newton's hypotheses, there was Albert Einstein, the famous physicist. Einstein did not explicitly discredit gravity. Instead, he stated that Newton's thoughts were one-dimensional. The general theory of relativity, proposed by Einstein, states that existence bends and gives rise to gravity. Einstein went one step farther and characterized the fabric of space and time as a sheet with twists, where a weight surpasses an edge. Besides, he stated that a clock set within the Earth's gravitational field on its surface would run slower than a clock set outside its orbit, where the laws of gravity no longer applied. Gravity, which was subsequently shown to exist between two objects regardless of whether they are planets in orbit or two marbles on a tabletop, is governed by the inverse square law. According to this law, gravity is inversely proportional to the square of the distance between two objects and is directly related to their masses. The speed of light in a vacuum would remain the same for a spectator from outside. According to Einstein, who also claimed that the laws of physics applied to everyone not moving faster than light, reality is indeed the very same thing as the space-time continuum, and gravity results from a twist in this continuum. Gravity is not a force. Thus, the explanation of Newton's thoughts by Brian Cox, despite Newton being viewed as one of the greatest physicists in history, shows that the contemporary physics community does not precisely regard him among those in that circle. This includes Brian Cox, who explained that although there are those who believe Newton was lying about gravity, he didn't fully characterize the evident power. Cox argued that Newton was merely trying to provide an explanation for a fundamental idea that was well understood and accepted. Now, one explanation for the indifference towards Newton's era was the greater predominance of religion over science. Newton was a religious man. Nevertheless, he couldn't, or perhaps didn't want to, continue developing the hypothesis of gravity beyond a simple explanation of the power. According to Cox, when pressed to explain gravity, Newton simply stated that its existence suggested a conscious element has authority and controlled the planets and the solar system. That was the extent to which Newton was willing to go. Consequently, how should one overcome gravity and undermine the principles of physics, which include the laws of time? It truly is simple to live on Earth. You need to really resist the principles of physics. The uses of time, widening, and time dilation as characterized by the theory of special relativity, fundamentally show that a clock that is very still and moving in an inertial frame of reference will tick more slowly than a clock that is fixed. The theory of time dilation could propel time travel if it were put to use. In theory, travelers in a fast vehicle could reach their destination a few moments sooner than those at rest. Only the theories of general relativity, which depend on gravity, or special relativity, which is based on relative speed, can explain why this is possible. The International Space Station pursued the decision to test this thought by sending humans in a fast-moving vehicle around the Earth. Although the experiment was successful, it only demonstrated that the astronauts felt a 20-millisecond delay in time. Remember that advanced technology has certain limits. Einstein used the concept of a light clock to describe his theory of relativity. When he first proposed it, a light beam is discharged, and it appears to be traveling in a straight line to an observer moving at the speed of light. When it bounces off two surfaces, an observer at rest or another person outside that perspective would perceive the light beam as having a greater distance to cover. According to Einstein, the speed of light is the only constant, regardless of how fast something is moving, especially concerning the laws of gravity. All other laws of physics are rendered ineffective in this regard. Thus, time is not a constant and can be extended to suit your needs, according to the theory of relativity. When two events happen simultaneously, an individual moving relative to them may perceive those events differently from someone observing the event from a fixed position. Applications of special relativity in everyday life are numerous. During his lifetime, two applications of special relativity were made possible by Einstein's theory: the twin paradox and length contraction. According to the twin paradox, if two twins are separated such that one is sent rushing into space beyond Earth's gravitational field, the other would return to Earth much older than the one who traveled. The original time dilation provided an explanation for this, implying that the spaceship's internal clock was running more slowly than the natural clock. Consequently, time appeared to slow down for the twin on board the spaceship, permitting it to progress by a few moments compared to the sibling on Earth. Well, this thought is truly charming. It hasn't anyway been experienced in standard events. On the other hand, the hypothesis of length compression has useful ramifications. While perhaps not exactly in the mind-bending way one could trust in vision, this guideline applied to a quick thing like a race vehicle. When a race vehicle passes you at a rapid speed compared to its valid speed, your psyche causes it to seem more modest than it is. However, there is a contrast between your impression of the vehicle and the genuine vehicle, which is recognizable. In any case, if you could see something going at the speed of light, this would seem to be considerably more fantastic. Do you know of any real-world uses of Einstein's theory of relativity, something that you may be utilizing right now? Systems for GPS navigation. GPS systems use flags that are traded back and forth between your gadget and satellites circling the Earth to determine your exact location. Except for a very little wiggle room, most GPS systems are incredibly accurate. It's essential to remember that these satellites are circling the Earth in space, where the gravitational draw of the planet is incredibly less. Imagine briefly that the theory of relativity wasn't made sense of. So, what would happen? Above all else, there would have been no such thing as a very accurate route system with real-world applications. Second, regardless of whether they existed, they wouldn't be helpful since they would be mistaken. It's challenging to imagine a world without navigation systems, and the only reason we have them and use them successfully is because the organizations that send off satellites into orbit account for relativity, which allows them to reliably gauge the impacts of time dilation and produce solid results. The general relativity hypothesis, almost 10 years later in 1915, was published by Albert Einstein. This hypothesis legitimizes that gravity is a consequence of mass extending the space-time fabric, disproving the thought that gravity is a natural force that exists in all that possesses mass. You would have to picture the universe in 4 dimensions, 3 for space and 1 for time, to appreciate general relativity. Imagine now that each point in this 4-dimensional universe could contain planets, stars, or even ordinary individuals. Naturally, they would have the option to bend or expand the space-time aspects just by virtue of their mass. Gravity, or if nothing else, our understanding of gravity starts from this arc. As indicated by Newton, gravity is a natural force that the Earth has and is responsible for coordinating everything toward its center. According to Einstein, space and time work as a fabric, and that is why objects are drawn toward the center of the Earth rather than by a force. Here's a better method for envisioning this image: a long trampoline. Now picture putting a bowling ball on the trampoline at an inconsistent area. It is clear that the bowling ball's mass is exactly adequate to cause a dimple in the trampoline. Step over to the trampoline and throw a stone onto it. Then what happens? The marble rolls naturally in the direction of the dimple the bowling ball made. You will see that heavier things, like tennis balls, don't fall around the dimple made by the bowling ball as easily as the marble did when you gradually begin replacing the marble with them. Likewise, if you drop something with a huge and similar weight to the bowling ball, for instance, another bowling ball, it wouldn't go toward the dimple made by the first bowling ball. Rather, it would create its own. This is a distorted explanation of what happens when we consider the smooth pathways governed by the fabric of space and time. The Moon is our natural satellite, and the space the Earth made just draws the Moon toward it, permitting it to remain in its orbit. The Moon's weight is clearly inadequate to resist the draw of Earth's gravity, yet sufficient to allow it to exist in its own space on the fabric of space and time. This is the only reason it isn't falling freely, like how the Earth might be attracted to the dip created by the immense Sun. It is kept from collapsing into the Sun by its significant mass. Therefore, Newton's gravitational regulations overlooked the genuine impacts of gravity and how they influence our climate. A valuable utilization of general relativity was exhibited in 1919 during a solar eclipse. Since they are sufficiently gigantic to escape the bend of the Sun, stars fall freely. However, a lighter star finds itself trapped in the Sun's orbit. Due to this, the Sun's rays are hindered from reaching Earth, resulting in a solar eclipse. How time is impacted by gravity. Einstein used certain cosmological constants in his estimations to establish the association between the general theory of relativity and our universe. It was only after much later that it was understood the universe is continually expanding instead of remaining static. Then, Einstein described this as his most significant blunder to date. Anyway, the Big Bang and the wave effect are two common events that are explained by the theory of general relativity. Albert Einstein proposed that heavy objects cause expanding influences in the fabric of our universe as they traverse existence. This is maybe something you still remember. General relativity gives an explanation for how the universe developed from an extremely hot and dense condition. The idea describes how Einstein's well-known equation, matter and energy, impacts the mathematics of the universe and addresses the expansion of space and time. Following his amendment of his equation to represent the universe's continuous development, Einstein came to the conclusion that specific universes are divided by the universe's expansion. This lined up with observational data gathered around the same time as the distribution of Einstein's thoughts. The general relativity equations of Einstein help in our understanding of the properties of the early universe. They provide an explanation for the origin of our infinite cosmos and lend credibility to the idea of a primordial singularity. Quite possibly, one of the most essential concepts in Einstein's general theory of relativity is the possibility of a wave in spacetime. It follows that massive objects like black holes and stars have the capacity to cause the spacetime fabric to bend around them. On the other hand, they are non-fixed objects that can produce gravitational waves when they accelerate or interact significantly with other gravitational fields. These waves are referred to as waves in the reality continuum. In like manner, assuming something were to disturb the space-time fabric ought to cause swells in space, which are what we presently allude to as gravitational waves. These waves can travel through space at the speed of light, conveying with them information about moving gravitational fields. Despite the fact that gravitational waves were guessed long after Einstein distributed his general hypothesis of relativity, they weren't numerically affirmed until 2015. They were affirmed in 2015, 100 years after Einstein's 1915 forecast by the laser-based LIGO ground-based observatory. This latest finding exhibits that they are more normal and can be identified at far longer frequencies. Another time in observational cosmology was introduced in 2015 with the weighty location of gravitational waves by the Laser Interferometer Gravitational Wave Observatory, LIGO. This thought was named the expanding influence, in light of the fact that, on a fundamental level, it looked like the wave that outcomes from dropping something into a still lake. From the disturbance-causing object, the waves emanate outward. This hypothesis has made it more straightforward for researchers to distinguish cosmic events like black hole and neutron star crashes today, by providing a brief look into the imperceptible. This also added to our developing appreciation of the universe. The issue of ordered security. Yes, the vast majority concur with Einstein's speculations. That doesn't mean, however, that the physics community hasn't talked about and refined Einstein's speculations of relativity or other reasonable speculations. Stephen Hawking proposed the order security theory in 1992. The thought was introduced by Professor Hawking in a recent study where he noted it appears that there is an order assurance office which forestalls the appearance of closed time-like curves and thus makes the universe all right for students of history. Professor Hawking is a very dry jokester, and following quite a while of attempting to sort out why time was not as steady, Einstein fostered this hypothetical proposition to make sense of time travel. Time loops and in backward time travel are hypothetical prospects. As indicated by Stephen Hawking, this speculation assisted individuals with understanding the impediments and potential impacts of the ordinary standards of physics. Sci-fi and science fiction writing have widely analyzed the idea of time travel. For his part, however, in trying to foster helpful time travel applications, Stephen Hawking routinely acknowledged thoughts relating not exclusively to time but additionally to the guidelines of modern physics. The sequence assurance guess proposes that closed time loop creation is forestalled by the regulations of physics. These are basically self-reinforcing pathways across spacetime that empower objects or data to travel back in time. General relativity has been adjusted in Stephen Hawking's idea, reviewing that Einstein proposed the hypothesis of gravity, which expresses that huge things like stars and black holes cause an ebb and flow in reality that draws other objects toward them. While considering the impacts of closed time loops on the construction of causality, the physicist's guess is significant. In the event time loops were allowed, one might envision situations in which an occasion influences its own earlier event. This prompts oddities such as the grandfather paradox, where it is feasible to forestall one's own presence by changing previous events. As indicated by Hawking's sequence assurance guess, the arrangement of time loops, otherwise called closed time-like curves, is normally forestalled by the rules of physics. Despite the fact that it hasn't been completely demonstrated, it delineates the idea that the universe has safeguards set up to safeguard causality. This involves keeping away from conditions in which previous events influence the present, as this could bring about puzzling conundrums and disable our cognizance of space and time. The Big Bang hypothesis, which hypothesizes that singularities such as those found in black holes are forever hid from outside eyewitnesses by event horizons, is a key part of this guard. If this hypothesis is correct, it could go about as a vast security net, forestalling the making of time loops that could prompt causality infringement. The sequence insurance guess of Stephen Hawking has left the physics community totally dazed since this physicist's 1992 show at the Significant Physics Show. It has been examined and tested. There are multiple approaches to respond to Hawking's sequence security guess. Interest, doubt, and examination, despite the shortfall of hard proof, have started clever discussions and new lines of inquiry. A few physicists have commended its endeavor to handle time travel-related issues in everyday relativity, exhibiting Hawking's normal interest. However, it is under examination since certain scholars question its generalizability and contend that closed time loops might in any case emerge in specific circumstances. Hypothetical and trial work is continuously being finished in the pursuit of a total knowledge of time. The order assurance guess is addressed by hypothetical physicists as they explore options to Einstein's conditions. Others, however, concentrate on conceivable quantum consequences for transient elements by diving into quantum mechanics. The reaction from the physics community is demonstrative of the complicated and dynamic examination concerning the idea of time in the universe. Contemporary speculations of time travel, Despite the fact that there will constantly be contentions and debates inside the academic community regarding whether time is a construct or an express that is continuously changing, contemporary physicists can concur that time doesn't stream consistently. Rather, it's a dynamic that relies upon both gravity and speed when we consider objects of huge mass and impressive speed, objects in the universe. The thought that time can be changed takes on a lot more noteworthy interest. Researchers working today have been attempting to find out more about black holes and how things pass through them. They have recognized and found the event horizon, which is the district encompassing a black hole's edge, as it were. This is the end of the street. Analysts have underscored that, due to a black hole's comprehensive nature, even light moving at incredibly high rates would not have the option to get away from it. Time dilation is a mind-boggling subject that gets distorted while examining the twin paradox or applying it to GPS frameworks. As per contemporary science, one can completely appreciate and partake in the capability of time dilation and, by extension, time travel in closeness to a black hole. As of right now, no one knows all that can be found inside a black hole. The main thing they are sure of is that simply customary conceptions of reality separate past the event horizon. Many individuals have even proposed that those that close the event horizon, time can stop. Contemporary physics coordinates ideas from relativity, quantum mechanics, and cosmology to give a complex and multi-layered comprehension of time. The single clear thought of time as a general ticking clock has given way to a unique, structured origination where time is straightforwardly connected with the design of the universe. Researchers and intellectuals are still entranced by the examination of these contemporary thoughts since it opens up additional opportunities for fathoming the substance of life. Do you still believe much must be found, or do you think the idea of existence is as direct as we initially suspected? Let us know in the remarks underneath. I appreciate you seeing. We'll see you with another video soon.